Folks, on this video, we're going to pick up with questions 9 through 11. And here they've given us three groups, group 1, group 2, group 3, and they've given us an electron configuration. That is a little bit different than an orbital notation. If you remember, orbital notations were the ones where they drew the orbitals with the arrows in the boxes. Arrow up is an electron spinning one way, arrow down is an electron spinning the other way. In this class, we learned to put the third quantum number above the box. The magnetic quantum number goes above the box, where this is 0. 0, when you have the middle box is always 0. That's the third quantum number. The third quantum number puts you in a box, which we call an orbital. The first and second quantum numbers are underneath the boxes. The first quantum number is the number you see. The second quantum number, if you remember, dealt with the letter of the sublevel. So when you were in the S, the second number was a 0. When you were in a P, the second number was a 1. But when we just write this part that's underneath the box by itself, it's called an electron configuration, which is a type of an electron configuration. The same way that an orbital notation, that's the one with the boxes and the arrows, is a type of electron configuration. A dot diagram is an electron configuration. Electron configuration is just configuring where the electrons are. So they want to know which one has the highest or greatest affinity in group 1. Let's take a look. These are all on the second level of the periodic table of elements. They are on period 2. All those elements are on period 2. Carbon's right here. Nitrogen's right here. Neon is right here. So with that in mind, we don't really have to worry about a ton of things. We don't have to worry about shielding effect or whatever, because they all have the same shielding effect. They're on the second level, so they have one level shielding. So what factors are going to influence their affinity? In other words, how much energy they release when they receive an electron, what factors will matter? Well, left to right, electron affinities tend to increase, but not uniformly. So we could say lithium has a lower electron affinity than fluorine. That is true. But an electron affinity doesn't matter just on size alone. Left to right, they get smaller. Why? Because we're increasing the atomic number. The smaller an atom is, the better it is at attracting and holding an electron, which would give it a higher affinity. But another factor that matters is stability. Stability. What are the four factors that influence? Here's the four factors that influence electron affinity. Stability is a huge one. Letter C there. So what makes an atom more stable when it gets an electron? First of all, it's made more stable if you can complete the octet rule. If that electron can fill that P sublevel, that would greatly increase electron affinity. But none of these here are halogens. The halogen in that row is fluorine. The halogens, if we look down on this chart right here, the halogens have the highest electron affinities. If you notice, they have the biggest columns here, because if you give them one electron, they would become stable like the noble gases. Look at the noble gas neon. It has a positive affinity. It has no affinity at all for an electron. Why? It's already stable. We can cross letter C off. That's not going to help neon at all. Look at nitrogen right here. If we give an electron to nitrogen, it would go from P3 to P4. The P sublevel, as we see right here, holds 6. When there's 3 in there, it's half filled. When we look back here to this thing, a half-filled P, D, or F offers some stability. Not a half-filled S, a half-filled P, D, or F. The sublevels that are made of more than one orbital. If you can half-fill them, it gives it a little bit, not a lot, it gives it a little bit of stability. So nitrogen, if we give it an electron, we ruin it from being P3. For that reason, nitrogen, look how low. Nitrogen's way down there underneath that yellow line. It goes carbon pretty high, drops way down to nitrogen, and comes up again for oxygen. Why does nitrogen have a 0 or actually a positive affinity? Because we ruined the P3. Take a look at the other one on this row. Carbon is a P2. If it gets an electron, it becomes a P3, and that is better than a P2. P3 is half filled. So which one in group 1 has the high affinity? Carbon does, letter A. Why? Because carbon would become a half filled, which gives it some stability. Not a lot of stability, some stability. Group 2, let's look down this line. Well, here we go. If we give 1 to potassium, it would become S2. If we fill that S, what happens? We look over here. A filled S, fully filled S, P, Ds, and Fs gives some stability. So calcium stability will improve, which means its energy can drop. A lot? No. But it would improve some. Potassium, number 19, it would improve some. Calcium, on the other hand, is already an S2. That is already some stability. So if we give an electron to calcium, it would become an S2P1. That would ruin it being an S2. Being an S2, as we see here, is better than not being an S2. It's some stability. So calcium wouldn't be helped much. It would actually be hurt a little bit by getting an electron. If we look down on this chart right here, look at calcium. It is a lot lower than potassium. It has a very small affinity for that reason. We continue on up. And you don't need those charts to know what the affinities are. You don't really need those charts. What about zinc? 30. Zinc's D is full, D10. A filled D is somewhat stable, a little bit more stable. Not fully stable like the octet rule, because its P's not full. But zinc would be ruined as well. So we would ruin zinc, we would ruin calcium. Potassium's the only one that could be helped. Letter A. Letter A, potassium could be helped. We look down here. Where was zinc on this chart? You didn't need the chart. We just needed to know it had a D10. Look at how those are right at 0. Those have no affinity for another electron. We would ruin it being a D10. Finally, what's the next one? Number 11. We're looking at group 3. Manganese is a D5. How many does the D hold? Well, we know the D sublevel is made up of 5 orbitals, each holding 2 for a total of 10. So manganese is half full. What do we know about a half-filled D? A half-filled D is better than a not half-filled D. So manganese is not going to want an electron. It would ruin that little bit of stability. We come down here and we find manganese. Look at it. Can you even find manganese? It's down here. It has 0. Chromium has some affinity for a new electron. It is negative. Why? Because it would go from D4 to D5. It would half-fill chromium. Scandium has 1 in the D, titanium 2 in the D, vanadium 3 in the D, chromium 4 in the D. We give chromium 1, its stability would go up. Manganese already has 5. We give it 1, we would mess it up. Now we've got a little bit of problem here. Germanium's P2. We learned that the P sublevel is half filled with 3 because it holds 6. So if we give germanium 1, it would half fill the P. So germanium would want 1. We look down here, look at germanium. Yep, germanium's up there, it does want 1. But what's the next element here? The next element is bromine. Bromine has 5 in the P. If we give bromine 1 more, it would have 6 in the P. 2 in the S and 6 in the P. 2 and 6 is 8. The outermost level is 4. So how many valence electrons does bromium start with? Well, the outer level is 4. 2 in the S, 5 in the P. 2 and 5 is 7. If we give it 1 more, it would have 8. It would satisfy the octet rule. You can't get any better stability than that. If we give bromine 1, it would be ecstatic. It would become so much more stable. The teeter-totter of stability and energy. You give bromine 1 more, that side, the stability side would go way up, so the energy side of the teeter-totter would go way down. Look at how big bromine's affinity is. It is up there with chlorine. Chlorine's the highest of them all. All right. Without a doubt, bromine would want it the most. It would have the highest affinity. All right, we come down to here. Now we're supposed to rank oxygen, beryllium, chlorine, and sulfur in order from lowest to highest affinities. Lowest to highest affinities. And they gave us a little chart to look at here. Lowest to highest affinities. We know affinity tends to increase left to right, and it tends to decrease top to bottom. But with affinity, those tendencies depend a lot on configurations. So left to right, we would expect beryllium to be lower than oxygen overall. And it is. But it's a lot lower than we would even expect. Why? Beryllium is in the S2 column. If we give beryllium an electron, we would ruin it being S2. Beryllium actually has a 0 affinity, or even a positive affinity. We would have to add energy to get beryllium to take it. We continue this way. Here's oxygen. Oxygen has 2 in the S, 4 in the P. You give it one more electron and it would be close to satisfying the octet rule. It needs 2 to satisfy the octet rule, but it would become close to satisfying the octet rule. It would have a fairly high affinity. Now, oxygen is smaller than sulfur. So our tendency would be to expect oxygen, since it's smaller, to be better at attracting and holding an electron. If it's better at attracting and holding it, we would expect oxygen to have a higher affinity than sulfur. But it doesn't. And that's because oxygen is almost too small. Too small meaning that oxygen would have to be given a little energy to force that electron into it before it could release energy. Oxygen is small, its electron cloud is very dense. The electrons are close to the nucleus, not taking up much space. It only has 2 levels. So when we go to give oxygen an electron, initially it would take some energy to force that electron into oxygen's cloud. Negative, negative repel. The cloud's negative. The electron we're forcing in is negative. It would take some energy to force the electron in before oxygen could release energy. It's because that second period is almost too small. It takes force to overcome the electron repulsion. So sulfur's affinity is going to be a little more than oxygen's, because sulfur is a little bit bigger and it's easier to force the electron in. So it would take a less initial energy to force the electron in, and then sulfur can release energy as it gets closer to becoming stable. So sulfur's next. And if you look on the table here, you would see that. Why is oxygen right here below sulfur? Because oxygen's almost too small. Now it goes sulfur down to selenium, down to tellurium. So here is where it starts to decrease, because they're all big enough where it's not as hard to force the electron in. So the bigger they get, the less attraction they have for the electron that's being forced in. Finally, chlorine is to the right of sulfur. If we give chlorine 1, it will satisfy the octet rule. If we satisfy that octet rule, it can release a tremendous amount of energy. In fact, chlorine has the highest affinity of all, because when you give it an electron, it becomes stable like neon. It's S2P5. Give it 1, it's S2P6. 2 and 6 is 8. Octet rule. Fluorine also would satisfy the octet rule. But why does fluorine, who's smaller than chlorine, have a lower affinity? Because smaller, they should be able to attract it better and hold it, taking less energy. Well, it's because fluorine's too small. It would take some force to force that electron into the fluorine's cloud, which would use up some of that energy release. The trade-off won't be quite as high. High, but not quite as high. That takes care of questions 12 and 9, 10, and 11. In our next video, we'll pick up with question 13.